5 days ago, 4 laboratories finished reading a fingerprint 66 million years old. It was not a footprint or a fossil, but the chemical trace of a killer. Below a thin band of clay you find dinosaurs, and above it, none again. On the 17th of July, a new study named what that killer was made of, and the answer rewrites how it killed 3/4 of life on Earth. It did not kill mainly with fire or with the blast wave. Here is the one question that this entire story turns on tonight. We were wrong about what that killer was actually made of. So are we also wrong about what the next one would do? And could we even see it coming before it reached us? If a question like that grips you, subscribe and say where you are watching. Now, let us get into it. Part 1. The fingerprint that waited 66 million years. Let me rebuild this discovery as a physical process, not a headline. 66 million years ago, an object struck what is now Mexico. An object that fast does not touch down, it vaporizes on contact. A large chunk of the Earth's crust vaporized along with it instantly. That superheated material blasted up above the atmosphere and spread worldwide. Over months and years, it settled back down across the entire planet. It formed a thin, dark seam in the rock everywhere at once. Geologists call that dark seam the Cretaceous-Paleogene boundary layer. You have probably seen a photo of a striped cliff with one dark line. That single line is the receipt for the worst day in Earth's history. Let me make that receipt feel real for a moment. Geologists have matched that same line on continent after continent. The same dark seam, the same age, the same chemical shock. It is one of the few truly global layers we know. No local flood or eruption could paint a line worldwide. Only something that touched the entire planet could do that. So the layer itself is proof of a planet-wide event. That is why it became the boundary between two great eras. Everything before it is one world, and everything after is another. Below that line lie dinosaur fossils, and above it lies almost nothing. Stay with me, because that seam is what makes this whole study possible. Think of the boundary layer as a crime scene preserved in stone. The killer struck, and then the evidence settled over everything. It sealed itself into the rock and waited to be found. Most crime scenes fade within days or weeks. This one has held its evidence for 66 million years. That is the gift the impact left, without meaning to. It scattered its own remains across the whole planet, and in doing so, it signed a confession it could not erase. Our job, all these ages later, was simply to read it. When the object vaporized, its atoms did not vanish from the world. They mixed into that global clay layer and stayed locked inside it. So the killer is not truly gone, just smeared thin across the planet. For decades we could not read that smear with any real precision. We knew the layer was rich in a metal called iridium. Iridium is rare in Earth's crust, but common in asteroids and comets. That was the first clue, back in 1980, that something struck us, but iridium only tells you that something hit, not what it was. Here is where this new team did something genuinely clever with the clay. They went after a different element entirely, and they chased nickel. Not just how much nickel, but the exact isotopes of nickel. Isotopes are versions of one atom with slightly different atomic weights. Different meteorite families carry nickel isotopes, like different regional accents. Two people can both speak English, yet reveal very different hometowns. The precise vowels give away Glasgow, or Alabama, or somewhere else entirely. Nickel isotopes work the same way inside a primitive space rock. Two rocks can share the same elements in very different proportions. Those proportions record where in the solar system each rock was born. The team was led by Georgi Makatadze at the University of British Columbia. They measured that nickel accent in the ancient boundary clay with extreme precision. Then they compared it against every known family of space rocks, and the accent came back matching one narrow, very specific group. Carbonaceous chondrites of the CO class, also called Ornans chondrites. They are named for a meteorite that fell in France long ago. Let me name the places where you can touch that boundary today. In Denmark, it runs through a coastal cliff called Stevens Klint. In Italy, it threads through limestone gorges near the town of Gubbio. In North Dakota, it sits inside an ancient, well-preserved riverbank deposit. The same dark line appears on continent after continent, all worldwide. That global reach is exactly why the layer is so trusted. One local event cannot paint a single line across every continent. Only a planet-wide catastrophe can lay down a worldwide seam like that. The team drew their nickel signal from marine clays holding the ejector. They worked across labs in Vancouver, Paris, Brussels, and Vienna together. Reading nickel this precisely is closer to listening than to measuring. You are straining to hear one faint accent under ancient background noise. The ordinary earth rock around it shouts, and the impactor only whispers. Separating that whisper took instruments accurate to a genuinely stunning degree. And nickel was a smart target for one particular reason. Its isotopes differ cleanly between the major known meteorite families, so the signal, once extracted, points toward one specific home. The team pulled that whisper out of the noise and read it. The accent it carried belonged to the dry, primitive outer system. That result did not appear from nowhere in the year 2026. It was the payoff of a scientific chase that ran for years. Let me be honest about how hard that measurement really is. The clay is mostly ordinary Earth, with a faint trace of the killer. The Earth's own nickel drowns out the visitor's nickel signal, so the team had to separate the whisper from the raw. That means painstaking chemistry, done in ultra-clean laboratories. A speck of contamination could ruin the entire delicate result. Frédéric Moynier, a scientist in Paris, helped drive that chemistry. His group specializes in reading isotopes at extreme precision. Georgi Makatadze carried the analysis as the study's lead author. Together they pulled a clean nickel signal from the ancient mud. And that signal matched the dry, distant ceochondrites. It did not match the wetter carbonaceous types proposed before. It did not match the ordinary rocks of the inner belt. The accent was specific, and it pointed far from home. Now step back and see what this method really gives us. For the first time, we can fingerprint an ancient impactor by type. Not just asteroid or comet, but a named family of rock. That is a genuine leap in what old clay can tell us. And it turns a vague catastrophe into a specific identified event. So the clay is no longer a blank record of death. It is a signed confession, 66 million years old. Remember the word ornans, because it is about to become the whole problem. That rare little word changes what this object could do to a living planet, and what it changes points a spotlight straight at our own century. Part 2. The rock so rare it should not have hit us. One of the researchers did not reach for a grand scientific word. Philippe Claes, a geologist in Brussels, reached for a very human one. He called the object an oddball, and he was being literal. He said this class is nothing like the meteorites in museum collections. Let me put a hard number on how strange that really is. Every meteorite we have ever recovered breaks down into known families. Carbonaceous chondrites, this broad group, make up only a small share of falls. Out of everything that lands here, only about 1 in 20 even qualifies. The ceochondrites are a small fraction within that already small slice. We are not talking about 1 in 20 anymore, but far rarer. This is one of the rarest kinds of space rock we know. So Cleese said something that I think is the heart of this discovery. Being struck by such a rare, distant object shows how unlucky the dinosaurs were. Sit with that word for a moment, because it matters more than it sounds. Of all the objects that could have hit, the one that did was a freak. A remote, primitive, unusual body from the deep cold of the outer system. The dinosaurs did not lose to the ordinary odds of the sky. They lost to a rare card pulled at the worst possible moment. Hold that idea, because luck is going to return near the end. Let me explain what a chondrite even is, in plain terms. Chondrites are stony meteorites packed with tiny ancient beads called chondrules. Those beads formed in the earliest days of the solar system. They are some of the oldest solid material we can hold. Carbonaceous chondrites are the most primitive branch of that ancient family. They preserve the original chemistry from before the planets fully formed. In a real sense, they are frozen snapshots of the beginning. That is why scientists prize them far beyond their appearance. Now recall how few of them actually fall to Earth. Most meteorites that land are ordinary stony or metallic types. The carbonaceous ones are the rare, dark, primitive exceptions, and the CO branch is rarer still within that exception. These primitive rocks are in effect time capsules from the start. They formed before the planets and never changed much since. So they carry the original recipe of the solar system. Scientists chase them precisely because they are so unspoiled. A pristine sample tells you what the beginning was like, and this killer was one of those pristine ancient bodies. That gives the discovery a strange double edge. The object that ended an age was itself a relic of creation. It was as old as the solar system, and it ended a world. So picture the odds stacked against the dinosaurs one more time. The sky is full of common rocks that could have hit. Instead, a rare messenger from the deep outer system arrived. It carried a chemistry almost nothing else in the neighbourhood shares. That is what makes this identification land with such weight. It is not just a label change on an old story. It is a different kind of object than we long assumed, and a different kind of object can kill in a different way. That is the thread we are pulling on all night. Change the rock, and you change the murder weapon. Change the weapon, and you change who dies and how. This is why one rare word, ornans, matters so much. It is not a footnote for specialists to argue over. It reaches all the way to the fate of a living world. Now, why does the exact type matter so much for the killing? Because CO chondrites are, in the plain words of the researchers, dry. That one small word is about to reorganize this entire extinction story. Let me explain what dry actually means for a rock like this. It is not only about water, though water is part of it. Earlier candidates for this impactor were wetter types, called CM or CR chondrites. Compared to those, a CO chondrite carries roughly half as much sulfur. It is also stripped of other volatile elements across the board. Carbon, zinc and water are all far lower than in the wetter types. A CO chondrite is a lean, primitive, volatile poor rock from the dawn of time. That makes it scientifically precious, one of the least altered leftovers we have. But it also means it arrived carrying a very different chemical payload. And here is the hinge that the whole story turns on now. For decades, the leading explanation for the killing was sulfur. The idea was that sulfur formed a haze that cooled and poisoned the world. Sulfur was the villain, the smoking gun everyone pointed at, but a dry, sulfur-poor impactor delivered far less sulfur than the old models assumed. Let me linger on why a dry rock matters so much. Water, carbon and sulfur are the reactive world-changing ingredients. They are the elements that form hazes, acids and poisons. A wet, carbon-rich impactor would flood the air with them. A dry CO chondrite brings far less of that chemistry along. So the atmosphere after impact looks different than we assumed. Less sulfur haze and less of the acid rain that follows. That single shift changes which weapon did the most killing. And it took a rare rock to force that rethink. Consider how strange it is that we can know this at all. We are describing the chemistry of an object that no longer exists. It vaporized in a heartbeat 66 million years ago, yet its atoms, spread through clay, still testify to its nature. That is the quiet power of this forensic science. It lets a destroyed object give evidence long after its death. And the evidence here is unusually specific and clear. The impactor was dry, primitive, and rare beyond almost all others. Hold that profile, because it will describe a modern danger too. The rarest kind of killer, then, may be the hardest to stop now. Cleese put it bluntly, and I will paraphrase his careful wording here. The impact still caused the extinction, That basic theory holds firm. But sulfur from the impactor is now much less likely to be the smoking gun. When you pull sulfur off the table, something else has to take its place, and the researchers were direct about what they believe finished the job. They pointed to the dust, not the sulfur, as the real weapon. But dust was doubted for years, dismissed as too heavy to linger. So how did a dismissed suspect climb back to the top of the list? Part 3. Why the killer's chemistry rewrites how it killed. For years, one idea about the darkening sky sat above the rest. To see why it fell, meet the 3 suspects for blocking the sun. Suspect 1 is sulfur, and it long held the leading role. When the impactor hit, it did not only vaporize its own body, it also vaporized the ground, and that ground was rich in sulfur. The Yucatan bedrock held thick beds of sulfur-bearing sedimentary rock, so even a dry impactor would release sulfur from the target itself. That sulfur rises and forms tiny reflective droplets high in the air. Those droplets bounce sunlight back to space, cooling and dimming the surface. They can also fall later as acid rain across land and sea. For decades, sulfur wore the crown as the primary global killer. Suspect 2 is soot, the black carbon born from enormous wildfires. The impact and the falling debris set forests burning across the land. Those fires lofted thick soot that also blocked the incoming sunlight. Soot has always played some part in this grim atmospheric picture. Suspect 3 is dust, the finely pulverized rock from the blast. The impact ground rock so small it measures millionths of a meter. That dust blasts up into the high atmosphere with everything else. Because the particles are so fine, they do not settle quickly. They hang, they drift, and they spread into one global veil. Hold those 3 suspects, because the balance between them just shifted hard. For years, dust was treated as only a minor supporting player. The thinking was that dust grains were simply too large to linger. They would supposedly fall out within weeks, or a few short months. Sulfur, being finer and longer lasting, kept the top billing instead. That was the settled scientific consensus for a very long time, but 2 separate discoveries have now overturned that comfortable old ranking. The first concerns what the impactor itself was actually made of. A dry, sulfur-poor CO chondrite delivered far less sulfur than assumed. Take the sulfur down, and another suspect must carry that lethal weight. Let me say that plainly, because it is the pivot of the science. Less sulfur in the rock means sulfur cannot be the main killer. The second discovery went and measured the dust itself, grain by grain, and it found the dust was much finer than anyone had thought. Fine enough to hang in the sky for years, not weeks. Put those 2 findings together, and the old ranking flips completely. The dismissed suspect, the humble dust, moves to the front of the line. Let me be fair to the other 2 suspects, though. The truth is almost certainly a blend of all 3. Sulfur played a part, and soot from the fires played a part. The dust did not act entirely alone up there, but the balance among them decides the shape of the winter. More sulfur means a sharper, shorter cold snap. More fine dust means a longer, deeper, darker famine, and the new chemistry pushes that balance toward the dust, so the killing was likely slower and longer than once thought. Not a quick chemical shock, but a drawn-out starvation. That distinction is not academic, because it decided who lived. A short cold snap spares more than a 2-year night, so which suspect dominated truly matters for the death toll. And the composition study just tipped the scales for us. It took the sulfur down and lifted the dust up. It made the slow, patient killer the likeliest one. That is why 5 days of news matter for an ancient event. A single measurement reshaped how we picture the dying. Not a fast poisoning, but a long grey starvation. The change is subtle on paper and enormous in meaning. It is the difference between a bad year and a dead world. And the evidence now favours the most patient killer of all. This is the misdirection at the centre of the whole extinction. The loudest part of the event, was never the deadliest part. You will see that pattern again later, and it will involve us. Let me explain why particle size decides everything about this fight. A grain of sand falls out of the air within seconds. A slightly smaller particle takes minutes, or perhaps a few hours. But a particle a few millionths of a metre across barely falls. Air currents lift it high and hold it there for years. That is the difference between a cleared sky and a dead world. Coarse debris drops out fast, and within weeks the light returns. Fine debris lingers, wraps the globe, and dims the sun for a decade. The lethality was not only in how much material went up, it was in how finely the impact ground that material down. Think of it as the difference between gravel and talcum powder. Gravel rains back down, but powder floats and refuses to leave. The violence of the impact milled rock into that floating powder. It built its own perfect murder weapon out of the ground. Now add the ocean into this darkening picture as well. At the sunlit surface of the sea drift tiny floating plants. That plankton is the base of the entire marine food web. Cut the light, and that base collapses across the whole ocean. Everything above it, all the way to the giant predators, starves, so the veil does not only chill the land, it reaches into the sea and switches off its engine too. Let me add one more layer to this darkening sky. Scientists measure how much a haze blocks light by its thickness. A thin haze dims the sun a little, like light cloud. A thick haze can turn noon into a deep grey dusk. The plume from this impact was thick beyond anything in memory. For a time, the surface may have received almost no usable light, and a plant cannot photosynthesize in a permanent dusk, nor can the plankton at the surface of the sea. So the veil does two brutal things at the same time. It chills the whole planet toward an instant ice age, and it starves the base of every food chain at once. The cold alone would have been a disaster on its own. The darkness alone would have been a disaster on its own. Together, they are how you empty a living world. That is why the fine dust rose from suspect to prime mover. It is the one agent that does both, everywhere, for years. But to feel what that dust did, you must first meet its maker. So let me rebuild the object itself, and the place it was born, because its birthplace is far stranger than almost anyone once expected. Part 4. The mountain that fell from beyond Jupiter. I want to give you a body to picture, not an abstraction. So far, this killer has been a fingerprint smeared in ancient clay. Let me turn it back into a solid object falling through space. Start with size, because the size alone is hard to hold. The impactor measured an estimated 10 to 15 kilometers across, that is roughly 6 miles wide, moving as a single mass. Those numbers are easy to say and very hard to feel. So let me translate 15 kilometers into something your body understands. 15 kilometers is taller than the altitude where airliners cruise. Picture that object standing on the ground beneath your feet. Its top would sit up in the lanes where jets fly. It was, quite literally, a small mountain loose in space. A mountain attached to nothing, falling toward a living world. Now take its speed, which is even harder to picture. It struck the Earth at around 64,000 kilometers per hour. That is roughly 40,000 miles per hour at the moment of contact. That is somewhere near 50 to 60 times faster than a rifle bullet. At that speed, the whole atmosphere is crossed in a couple of seconds. There is no warning a human eye could ever act upon. By the time the sky brightened, the event was already over. Stay with me, because the next detail is where this turns cosmic. Where did this rare dark rock actually come from? This new study did not answer that origin question alone. In 2024, a separate study chased a metal called ruthenium. The ruthenium isotopes in the boundary layer pointed somewhere astonishing, not the inner asteroid belt, where most of our impactors form. They pointed to an origin beyond the orbit of Jupiter, out in the cold, primitive, outer reaches of the solar system. That is where the carbonaceous bodies formed and mostly stayed. Christian Kuberl, a geochemist in Vienna, worked on that ruthenium study. He also worked on this new nickel paper 5 days ago. At the time, the door was left open on the exact type. The ruthenium could place it in the carbonaceous family, and far out, but finer measurements might someday narrow it to one meteorite class. This new nickel study is that someday arriving at last. It took the answer from broad family to one specific type, from carbonaceous chondrite, a blurry answer, down to CO chondrite, a sharp one. So here is the object, fully assembled in your mind. A dark, primitive, volatile pore rock, 10 to 15 kilometers wide. Born beyond Jupiter, in the deep freeze at the edge of things. There it probably drifted, undisturbed for most of the solar system's life. Then something nudged it, and the long fall inward began. I want you to sit with how blind that process really is. The solar system is not a finished, settled, orderly place. It is a slow game of gravitational billiards, still running today. Jupiter acts like an enormous stirring rod out among the small bodies. Its gravity nudges distant rocks onto new and dangerous paths. Sometimes it flings them outward, and sometimes inward toward us. There was no aim in it, and no malice at all. The object that killed the dinosaurs was not sent by anything. It simply fell, one rock among countless millions of rocks. It happened, by pure geometry, to cross Earth's path on one day. If the timing had been off by even a few minutes, we miss. The Earth moves on in its orbit and the rock sails past. The dinosaurs keep going, and you very likely never exist at all. That is how thin the margin was between two entire worlds. Let me sit with that improbability one more moment. This was a rare kind of rock, from a rare, distant place. It arrived on a rare path, at a rare, exact instant. Every one of those had to line up for the strike to happen. Change any single one, and the dinosaurs likely survive. The odds against this exact catastrophe were staggering, and yet it happened, and it reshaped all of life. That is the unsettling lesson hidden inside the luck. Rare does not mean impossible, it just means rare on a long clock. The universe has an enormous supply of these long-shot events. Given enough time, the improbable becomes the inevitable. So the dinosaurs were not cursed by any design. They were on the wrong end of a long roll of the dice. And the dice are, in a sense, still rolling above us. There is an older debate hiding behind this whole question. For years, some scientists argued the impactor was a comet. A comet is an icy body from even further out than the belt. A cometary strike would mean a different origin and chemistry. The isotope work, the ruthenium and now the nickel, weighs against that. The evidence leans hard toward an asteroidal carbonaceous chondrite instead. So, the balance has swung, though the question stayed open for decades. I mention it so you see how hard-won this answer is. We are reading a killer's identity from atoms in old clay. Every refinement in our instruments reads a little more of it. Now picture the final approach of this dark, primitive mountain. It had drifted in silence for most of the solar system's history. Then, it crossed the inner system on a path toward one blue world. It did not slow in the atmosphere the way small meteors do. It was far too large for the air to matter at all. To an object that size, the atmosphere was barely even there. For a small meteor, our air is a thick, protective shield. It burns up most rocks long before they reach the ground. That shield is why most shooting stars never land, but a 15-kilometer mountain does not notice the shield. The air that stops a pebble is nothing to a mountain. So this object felt no braking, no burning, no resistance. It arrived at the ground with nearly all its speed intact. That is part of why the energy was so unimaginable. Nothing slowed it, and nothing softened the blow. It punched straight through and reached the crust in a heartbeat, and in that heartbeat, an entire world began to end. Now hold on to one more feature of this rock. Its colour. Carbonaceous chondrites are dark as charcoal in many cases, A dark object reflects almost no light back into space, and an object that reflects little light is very hard to see. I am putting a pin in that fact right now. Later, that single dark detail is going to change how you feel about the sky. But first, we have to survive the first hour after it lands. Part 5. The worst hour the planet ever had. Let me walk you through the first hour, not to horrify you. You cannot understand the aftermath without feeling the energy released first. A 15-kilometer rock at that speed behaves like nothing in our experience. The energy released has been estimated in the billions of Hiroshima bombs. Not thousands, not millions, but billions, delivered in a single instant. All of it landed at one point on the Yucatan Peninsula. Let me slow the first few seconds down, frame by frame. At contact, the rock and the ground did not merely heat up. They ionized into a core of superheated plasma at the strike. That plasma reached temperatures above 10,000 degrees Celsius. That is hotter than the visible surface of the sun itself. Within seconds, the impact dug a hole over 20 kilometers deep. It hurled molten bedrock up and out of the atmosphere entirely. The crater it left spans roughly 180 to 200 kilometers. You could not see one rim from the other standing inside it. It lies buried now under the Yucatan and the shallow sea offshore. That burial is why we only confirmed the crater around 1990. But it is there, the unmistakable signature of the blow. Stay with me, because the object struck a shallow sea, and striking a sea means it did not only throw rock, it also launched an almost unimaginable amount of ocean water. In 2022, a team ran the first full global tsunami simulation. Scientists from the United States agency NOAA helped lead that work. The numbers they produced are genuinely difficult to hold in your head. About 2.5 minutes after impact, a rim wave rose. That wall of water stood roughly 4.5 kilometers tall, nearly 3 miles of ocean, standing up as one moving wave. 10 minutes in, that wave had spread past 200 kilometers out. It still stood around 1.5 kilometers high there. Hold that number, because a comparison is coming that makes it worse. The total energy of that tsunami dwarfs anything in human memory. It measured around 30,000 times the Indian Ocean tsunami of 2004. That earlier tsunami, in December, killed more than 230,000 people. Now multiply that horror by 30,000 across the ancient seas. The waves crossed whole oceans and scarred the seafloor thousands of kilometers away. We can still read those scars in the rock today. And then, strangely, the fire arrived from above, not below. All that rock thrown skyward had to come back down again. Billions of tons of debris rained back through the atmosphere worldwide. Friction with the air heated that falling debris to a glow. It turned the whole upper sky into something like a broiler. Picture an oven set to broil, but the size of the sky. That glowing sky radiated heat down for roughly an hour. Let me say that plainly, because it decided countless deaths. For about an hour, much of the planet's sky cooked the surface. That heat, with the hot debris, ignited wildfires across the land, not near the impact only, but on continent after distant continent. For a brief window, much of the world's forests may have burned at once. The ground itself shook with the force of a colossal earthquake. Estimates put that shaking near the top of the seismic scale. Let me give you one more image from those first minutes. The impact flung molten droplets of rock high above the world. They cooled into tiny glass beads as they fell back down. Those beads landed everywhere, a worldwide sprinkle of impact glass. We still find that bead layer across the globe today. It is part of how we read this event so clearly. The shaking, meanwhile, was almost beyond the ordinary seismic scale. Some estimates place it near a magnitude of 11. For comparison, great modern earthquakes rarely pass magnitude 9. Each step up that scale multiplies the released energy enormously. So an 11 is not a little worse than a 9. It is a different order of violence altogether. Near the impact, the the solid ground behaved almost like a liquid. Rock flowed, rebounded, and froze into strange ring shapes. Those buried rings are part of what later betrayed the crater. All of this unfolded within minutes of the first contact. The planet had never taken a blow remotely like it. Let me try one more comparison for the energy released. Gather every nuclear weapon ever built by every nation. Detonate all of them together in a single place at once. That combined blast would still fall far short of this impact. The strike carried the force of many millions of such arsenals. It is genuinely hard for the human mind to hold that. So do not try to hold the number, just hold the effect instead. Now recall what the object actually struck on that day. It hit a shallow sea over sulfur-rich sedimentary rock. That target rock vaporized along with the impactor itself, and that vaporized rock began the poisoning of the sky. So the ground it hit shaped the disaster that followed. Deep beneath the crater, the crust rebounded into a ring of peaks. In 2016, scientists drilled into that buried peak ring. They pulled up granite that had been lifted from far below. The rock recorded, in its very structure, the violence of the blow. It is one more page of the receipt left in the ground. Close to the impact, nothing living had any chance at all. For hundreds of kilometers, the land was simply sterilized. Picture the scene in those first terrible minutes. The air itself glowed, and the ground ran like liquid. Anything alive nearby was gone before it could react. There was no fleeing, and no sheltering, and no surviving. The only mercy was how fast it happened there. Farther out, the mercy of speed disappeared entirely. There, death came slowly, over months and years, and that slow death is the part that reached the world. Everything there died within minutes of the first contact. But that lethal zone, however vast, still had an edge. Beyond it, the world did not yet know it was dying. That gap between the local blow and the global death matters. It is the whole reason this story does not end here. So gather the first hour into one picture in your mind. Superheated plasma, a mile-high wave, a broiling sky, and global fire. That is the version of this day most people carry with them. The fire, the wave, the shaking, the sheer overwhelming violence. In that version, the dinosaurs die from the blow itself. But here is the truth the science has circled for years. That blow, as vast as it was, still reached only so far. And what happened next is the part that actually ended their world. Part 6. The thing that reached the far side of the world. I need to be careful and precise about one crucial point. The blast, the wave, and the fire were catastrophic, but local. Local does not mean small, so hold that distinction firmly. It means those effects reached hundreds, or a couple thousand kilometers. They did not strike every continent and every ocean uniformly. Picture a creature living on the far side of the planet. It did not feel the earthquake rolling out from Mexico. It never saw the great wave, which broke oceans away. It was not burned by the debris falling over its region. By raw impact alone, that distant creature should have survived. And yet the far side of the planet died too. That single fact is the deep mystery of this whole extinction. Let me frame the puzzle as sharply as I can. How do you kill 3/4 of all species at once? On every continent, in every ocean, top to bottom, including things living in permanent darkness on the deep sea floor. The blast cannot reach them, and the wave cannot reach them. The fire cannot reach the crab in the cold abyss. So something else had to travel, and travel everywhere. Something had to change the entire planet at the same time. And it had to hold that change in place for a long while, long enough that even the survivors of the first day failed. Hold that thought, because it defines everything that follows. For a long time, the answer to this puzzle was sulfur, a worldwide haze of reflective droplets, cooling and darkening the sky. For decades, that was a reasonable and widely accepted answer. But we just took a hard look at the projectile itself, and the projectile did not carry the sulfur we assumed. So we are left holding the real question of this story. If sulfur was not the main agent, what circled the entire globe? What reached every corner of the planet without fail? And what kept the lights off long enough to starve a world? Let me make the deep sea case even starker for you here. Some animals live where sunlight has never once reached them. They sit in cold black water far beneath the waves. No blast, no fire, and no wave ever touches them. Yet at the boundary, many of those deep creatures vanished too. Their food ultimately drifted down from the sunlit surface above. When that surface died, the slow rain of food stopped. So the deep starved, even though it was never burned. That is the reach the dust had, and the blast lacked. Let me hold on that deep sea image a little longer. Those creatures had no eyes for the fire in the sky. They felt no wave, and no burning wind ever found them. Their world was cold and black long before the impact, and still they died, quietly, as their food supply failed. That is how total a 2-year darkness truly is. It reaches places no explosion could ever touch. It kills by subtraction, by simply removing the sun. That is a different kind of weapon than a blast. A blast destroys what it touches, and then is gone. Subtraction takes away the one thing everything needs, and it takes it away from the whole planet at once. You cannot outrun it, because it is everywhere. You cannot hide from it, because it is the sky itself. The only defense was to need almost nothing for a while, and very few living things could manage that trick. No corner of the planet is safe from that subtraction. Now think about what kind of agent could do this. It must ride the winds around the entire turning planet. It must blanket the frozen poles and the hot tropics alike. It must stay aloft for months, and better still, for years. Sulfur seemed to fit that job for a very long time. Sulfur droplets are fine, and they do linger up high. That is why the sulfur story held for so many decades. But the impactor delivered less sulfur than that story required. So the case for sulfur as the main agent weakened badly. Meanwhile, the case for fine dust quietly grew stronger. Fine dust rides winds, blankets the globe, and lingers for years. It quietly checks every box the killer's profile demands. The dismissed suspect turns out to fit the crime perfectly. Let me sharpen the puzzle with a single thought experiment. Imagine you had to kill life on every continent at once. A bomb, however large, cannot do it, because bombs are local. A wave cannot do it, because oceans have far shores. A fire cannot do it, because fires need fuel and burn out. To reach everywhere, your weapon must travel through the air. It must ride the winds that circle the whole planet. It must spread until it covers pole, tropic, and everything between. And it must stay up there far longer than any storm. Only a fine, floating veil of particles fits that description. That is why the killer had to be something airborne and lasting. Sulfur was one candidate for that veil, and dust was another. For years we bet on sulfur and dismissed the dust. The new chemistry of the impactor reverses that bet. Less sulfur in the rock leaves the dust to carry the crime. And the dust, we now know, was ground fine enough to linger. So the weapon that reached the far side was the veil of dust. It is the quiet answer to a very loud event. And it explains the one thing a blast never could. It explains why the whole planet died, not just one region. The dust circled the globe and stayed there for years. It did not need to touch a creature to kill it. It only had to block the sun above every land and sea. That is a reach no fireball could ever match. So the loudest part of the day killed the fewest. And the quietest part of the aftermath killed the most. That reversal is the deepest lesson of this whole story. We fear the flash, but the flash is only local. We should fear the veil, because the veil is global. Hold that reversal, because it returns for us later. The answer is the dust, the humble suspect we once dismissed. And the dust is where an explosion becomes something far quieter. It is where the story becomes a planet wrapped in a sheet. So let me show you exactly what that dust does next, because the numbers behind it rank among the most chilling in science. Part 7. The 2 years the sun went out. In 2023, a study in the journal Nature Geoscience changed the picture. A team led by Sem Burke-Sennell went hunting for the dust directly. Several of them are the same people behind this new impactor study. They went to that well-preserved boundary deposit in North Dakota. The layer there is expanded enough to measure the fallen grains. So they measured the size distribution of the silicate dust itself, and they found the dust was finer than anyone had assumed. Much of it fell in a narrow deadly size range, roughly 0.828 millionths of a meter across. Let me put that size in a number you can weigh. Particles that fine do not fall from the sky in weeks. They linger, and that single property changes everything downstream. Then the team fed that dust into a climate simulation. They injected the fine plume into a model of the ancient air, and they let the physics of the atmosphere simply run. Here is what the model told them, and it is staggering. That dust could have stayed aloft for up to 15 years. 15 years of fine rock hanging in the high atmosphere. During the worst of it, the surface cooled dramatically. Global average temperatures may have fallen by as much as 15 degrees Celsius. That is a planet-altering Ice Age scale collapse in temperature. Let me anchor that number in something you can feel. The last great Ice Age was colder than today by roughly that much, and that colder world buried whole continents under ice. It took thousands of years to slide into that cold. The impact winter arrived in a matter of weeks. Picture the plunge into an Ice Age, but almost overnight. No time to adapt, migrate, or slowly adjust. The cold simply fell on the world like a lid. For warm-blooded and cold-blooded creatures alike, it was a shock. And it arrived not over centuries, but within a single lifetime. But the cold is not even the part that kills the most. Hold on, because this next number is the whole ballgame. The simulations showed photosynthesis shutting down for almost 2 full years. Let me say that again, slowly, because it decides everything. For roughly 2 years, across the entire planet, the light failed. Not enough sunlight reached the ground for plants to feed themselves. Not enough reached the sea for the plankton to survive. Picture a fine sheet thrown over the whole turning world. Not black, but thick enough to grey the sun into a smudge. The kind of light where you could not read outdoors at noon. Now imagine that sheet refusing to lift for 2 long years. Photosynthesis is how sunlight becomes food at the base of everything. It is what green plants do and what ocean plankton do. Take the light away and you do not just chill the world, you switch off the machine that makes food at the very bottom. Think of it as a dimmer switch on the sun itself. Someone turned that dimmer down to almost nothing for 2 years. Then they broke the knob off so it could not turn back. That is what a fine dust plume from this impact does. And it does it everywhere at once, because the dust wraps the globe. This is the agent that reached the far side of the world. This is what starved the crab in the lightless deep. Now connect the 2 studies, because together they lock the case. In 2023, the dust model said fine dust drove the winter, but a model is only as good as its inputs. One huge unknown was how much dust versus sulfur the impactor gave. That depended entirely on what the impactor was made of. And 5 days ago, the nickel study answered exactly that. A dry, sulfur-poor CO chondrite, delivering less sulfur than we thought. So the dust hypothesis does not just survive, it moves to the front. The 2 findings fit together like a key in a lock. The rock was dry, so the dust did the killing. Let me trace how that darkness actually kills, step by step. First, the light fails, and the green plants stop growing. The plant eaters lose their food within weeks or months. Then the animals that ate those plant eaters begin to starve. The collapse climbs the food chain, link by link, upward. In the ocean, the same collapse runs from plankton up to giants. Nothing is spared because everything ultimately eats the sun, and the cold makes every part of that collapse worse. A frozen, dark world offers no refuge and no easy prey, so the deaths are not instant, and that is the horror. They unfold over months and years of hunger and cold. The first day was violent, but the long dying was patient. That is the true shape of this mass extinction. Now here is why this new study matters so directly. The old models could not agree on how dark it got. The darkness depended on the mix of dust and sulfur, and that mix depended on what the impactor was made of. The dry CO chondrite tips that mix hard toward dust. More dust means a longer, deeper, more lethal night. So the composition and the climate models fit together at last. The rock was dry, and the dust did the killing. 2 studies, 2 teams, 1 answer clicking into place. That is how real science usually settles a hard question. Not with one grand proof that ends all argument, but with separate lines of evidence quietly agreeing. The dust study measured the grains and modelled the sky. The nickel study named the rock that made the grains. Neither one alone would have been fully convincing. Together, they point the same way with real force. The rock was dry, so the dust ran the winter. And the winter, not the fire, emptied the world. There is your real danger reveal, written across 66 million years. The audience comes for an explosion, a single violent instant. The reality is a slow starvation under a dimmed ash-grey sky. The fire was the opening act, over within a single hour. The famine was the main event, and it lasted for years. Recovery, when it finally came, was slow and strange to see. In the fossil record, one plant surges back first of all. The ferns rush in, the way weeds take an abandoned lot. Scientists call it the fern spike, the signature of a healing world. It marks the moment life began clawing back from the dark. But the giants were gone, and small survivors inherited the stage, which raises the obvious uneasy question you are probably already asking. Who exactly lived through that long night? And why them? Part 8. Who the darkness spared, and why? If a planet goes dark and cold for 2 years, survival is not random. The pattern of who lived tells you something about resilience itself. The same rules would govern any sudden collapse of the food supply. So let me lay out the 3 rules the darkness enforced. Rule 1 is brutal and simple. Size worked against you. Large animals need a great deal of food, and they need it constantly. A big, warm, hungry body in a dying world is an engine without fuel. Large animals starve first, because they cannot simply power down. The non-avian dinosaurs sat on the wrong side of that rule. Rule 2, the ability to shut down and wait, saved you. Some creatures can drop their metabolism to almost nothing. They can burrow, slow their bodies, and outlast a long famine. If you can hide in a hole for a season you might endure, many of the small survivors could do exactly that. Rule 3, not depending on living plants directly saved you. Think about what food remains after the plants have died. Dead matter, detritus, decaying leaves, seeds, and rotting wood remain. Food chains rooted in decay survived better than those rooted in growth. A creature eating dead material still had a supply when the green died. Think of a scavenger picking through the fallen and the dead. Its pantry did not vanish the instant the sun dimmed. It fed on what had already lived, not on new growth. So decay itself became a lifeline through the dark. The animals tied to decay outlasted those tied to fresh green. Freshwater rivers, fed by dead matter washing in, held up better. A river carries a constant supply of dead leaves and debris. That debris feeds insects, which feed fish, which feed others. So a whole food chain ran on death, not sunlight. Those chains bent under the darkness, but many did not break. The open ocean, by contrast, ran almost purely on sunlight. When its sunlit plankton died, it had no such backup. That is why the sea suffered more than the rivers. The open ocean surface, by contrast, collapsed almost completely. Now put yourself in the body of a survivor for a moment. You are small, and the cold has taken the world. You wake only to eat, then sleep to save your strength. You feed on seeds, on insects, on the fallen dead. You ask nothing of the vanished sun above you, and season by season, you simply outlast the dark. That patience, not power, is what carried life through. The meek did not inherit the earth by winning. They inherited it by still being alive at the end. Now let me make the casualty list concrete, by name. On the losing side, almost everything large and specialized died. The non-avian dinosaurs, the giants of the land, vanished entirely. The pterosaurs, rulers of the sky for 100 million years, gone in the seas. The great mosasaurs and plesiosaurs disappeared. The ammonites, coiled shellfish that filled the oceans, gone at this line. That lineage had survived for hundreds of millions of years before. It had lived through earlier catastrophes, yet this one erased it. And vast fractions of the ocean's floating plankton simply collapsed. When the plankton go, everything above them starves in turn. Now the survivors, and this is where it gets surprising. Crocodiles and their relatives came through the long dark alive. Many lived in those detritus-fed rivers that held up best. Turtles made it, and amphibians like frogs largely made it too. Insects came through in enormous numbers, as did small mammals. Our own distant ancestors were among those small waiting survivors. And here is the fact that reframes the entire extinction. The dinosaurs did not entirely die that day. One branch of them survived and is still here today. That branch was the birds, and every living bird is a dinosaur descendant. The sparrow at your window is a small, feathered dinosaur. The hawk over the highway carries that ancient lineage forward. They squeaked through the 2-year night and kept the line alive. When you look at a bird, you see what the dark left standing, so the pattern holds right down the entire list. Big, specialized, tied to the living surface world, and you died. Small, flexible, able to hide and eat the dead, and you lived. Let me linger on a few of these survivors and victims. The mosasaurs were huge marine reptiles, the sea's apex hunters. They had dominated the oceans, and then they were simply gone. The ammonites had drifted the seas for hundreds of millions of years. They had survived every earlier crisis the planet had thrown at them. This time, their floating young could not endure the dead surface. An ancient, resilient lineage ended in that long, dark famine. Now weigh that against the small mammals in their burrows. They were unremarkable creatures, living in the shadows of giants. They were warm, small, and able to sleep through hard times. They ate insects, seeds, and whatever the dark left behind. And so they lived, while the mighty starved above them. From those survivors, over millions of years, we eventually arose. Sit with how humbling that inheritance really is. We are not the heirs of the strong and the dominant. We are the heirs of the small things that hid and waited. The darkness did not choose the powerful, it chose the adaptable ones. And it left the adaptable a whole empty world to inherit. Let me show you the moment the world began to heal. In the rock just above the boundary, the pollen shifts. Suddenly it is dominated by the spores of ferns. Ferns are the weeds of a devastated landscape. They rush into bare, broken ground before anything else. Scientists call that layer the fern spike, a sign of recovery. It marks the first green returning to a scorched world. But recovery was slow, far slower than the killing. It took a very long time for richness to return. And when it did, the cast of characters had changed. The giants were gone, and the small had inherited everything. That is the strange gift buried inside the catastrophe. The birds inherited the sky the pterosaurs had ruled. The mammals inherited the land the great dinosaurs had held. An ending for one world was an opening for another. It reads almost like a moral, but deep time does not do morals. It does mechanisms, and the mechanism here was the dark, and that mechanism is exactly why the past reaches toward us now. because everything so far has been forensic about a vanished world. It is fascinating, and it feels safely finished, does it not? But that comfortable feeling is about to become the problem. Part 9. Are we actually overdue for this? This is the question sitting in the back of your mind. Let me deal with it head on and honestly. There is a reassuring version, and there is a panicked version. The reassuring version says Chicxulub was a freak, once in 100 million years. Go back to your evening, it says, the odds are nothing. The panicked version says the sky is full of killers, and we are overdue. Both of those are wrong, and the truth lives in the specifics. Let me hold both feelings at once. Honestly, yes, a true planet killer is genuinely vanishingly rare. And no, one is not lurking on our doorstep tonight. So the panic version overstates the immediate danger badly, but the reassurance version hides a real and present gap. Smaller strikes are not rare at all on human timescales, and those smaller strikes can still end cities or seasons. So the honest answer sits between comfort and alarm. We are safe from the giants for now. Very likely, we are not safe from the middle of the ladder, and that middle is exactly what we track worst. Here is the real structure of the threat above us. Space is not evenly dangerous, and size is the key. The danger and the frequency run in opposite directions. Small objects are common and hit often, but do little. Giant objects are rare and hit almost never, but end worlds. Let me populate that ladder with real, verifiable events. Start at the small end with the Chelyabinsk meteor. On the 15th of February 2013, it entered over Russia. The object was only about 20 meters across. It came in at roughly 40,000 miles per hour. It never even reached the ground as a solid mass. It exploded in the air, 20 to 30 kilometers up. The blast carried an energy of about 500 kilotons. That is dozens of times the Hiroshima bomb from a 20-meter rock. It shattered windows across an entire city below. The shockwave injured roughly 1,500 people. Most were cut by flying glass, and thousands of buildings were damaged. And here is the detail you must hold tightly. There was no advance warning of it at all. None. Now step up the ladder to Tunguska in Siberia. On the 30th of June, 1908, an object exploded there. It was probably 50 to 60 meters across. It burst in the air over a remote forest. It flattened an estimated 80 million trees. The devastation covered around 2,000 square kilometers. That is roughly 800 square miles of forest, knocked flat. The energy ran near 1,000 times the Hiroshima bomb. 50 meters did that, from a single airburst. Now hold both numbers as we climb one more step. 20 meters injured a city and broke its windows. 50 meters flattened 800 square miles of forest. And Chicxulub was 10 to 15,000 meters across. Not 50, not 500, but 10 to 15,000. The energy does not scale gently as objects grow. It scales with brutal, accelerating speed instead. So the gap between Tunguska and Chicxulub is not a step. It is a vast and terrifying chasm. Let me give you one more real event you can visit. In the Arizona desert sits a bowl called Meteor Crater. It formed around 50,000 years ago from a small impact. The object was only about 50 meters of solid iron, yet it punched a hole nearly a mile across. You can stand on its rim today and look down into it. A 50-meter rock did that and left it in the ground. Now imagine an object 10 times wider than that. Then imagine one 100 times wider still. The energy climbs far faster than the size alone. That is why the chasm between the events is so deep. A modest jump in size is a giant jump in destruction. The objects in that chasm are the ones worth watching. From a couple 100 meters up to a couple kilometers wide, they would not end all life on Earth. But they could end a city, a region, or a civilization. Let me put real numbers on how crowded that middle is. Astronomers estimate the small rocks near Earth number in the millions. In the Chelyabinsk Range alone, there may be 20 million of them, and of that swarm, we have spotted only around 500. 500 found out of a possible 20 million. Most are small enough to burst harmlessly high above us, but the frequency of the larger ones is what should focus you. A Chelyabinsk scale event happens somewhere roughly once a century. A Tunguska scale event happens perhaps every few centuries. These are not once in the history of our species events at all. They are once in a lifetime or once in a few lifetimes events. The only reason they rarely make headlines is simple geography. The Earth is mostly ocean and empty land, thankfully, so most of these airbursts happen where no one is hurt. Often, no one even notices them at all. That is luck, not safety, and the difference matters. We are not overdue for a planet killer, and that is true, but we are always about due for another Tunguska, and whether the next one bursts over sea or city is chance. Let me be blunt about what that chance really means. Somewhere out there, a Tunguska-sized rock has our name on it. Not soon, perhaps, but on the long clock, it is coming. The only question is when, and over what patch of ground. And right now, we would likely not see it in time. That is not doom at all, it is simply an unfinished job. The job is to find these rocks before luck decides. We have the ability to do it, if we choose to. Right now, that outcome is left almost entirely to chance, because we still cannot see most of them coming. Now here is the reassurance, and its immediate catch. The true planet killers, a kilometre and up, are mostly found. None of the known giants is on a collision course. Take real comfort in that, because it is genuinely earned. But do not relax, because the comfort hides a larger question. We have found the giants, yet the middle of the ladder is different. How many of those city killers and country killers have we actually found? And what if the ones we miss most are the deadliest kind? Because the colour of the Dinosaur-Killer points at exactly that gap. Pull the pin from the fact I left earlier, because this is where it goes off. The colour that hides a killer from every telescope. I told you the impactor was dark as charcoal. I told you a dark object is a very hard object to see. Now watch that single fact become the heart of the danger. The 2026 composition study is not only about the past, it is a warning about the present, written in the language of rock. Here is how we find asteroids, for the most part. Ground telescopes scan the night sky for moving points of light. The key word in that sentence is the word light. Those telescopes see asteroids by the sunlight the asteroids reflect. A bright, rocky asteroid throws back a decent share of that light. So we spot it moving against the fixed background stars. But a dark, carbonaceous asteroid reflects almost nothing at all. It can sit right there, the same size as a bright one. And it appears far fainter, or effectively invisible, to our telescopes. Let me say that plainly, because it is the whole problem. The composition that we now believe killed the dinosaurs is dark. And dark is exactly what our main detection method sees worst. The deadliest historical impactor is the type we are least able to find. Now let me put a number on how far behind we are. Back in 2005, the United States Congress set a task. It told NASA to find 90% of the large near-Earth objects, specifically those larger than 140 meters across. That size is the rough threshold for regional devastation. So where do we stand, 2 full decades later? By recent accounting, only around 44% have been found, not 90%, and not even half of them. More than 1 in 2 of those regional killers is still out there. Uncatalogued, its orbit unknown, its path a complete blank to us. Let me put that failure in plain, uncomfortable terms. We set a goal to find 9 in 10 of these objects. 20 years later, we have found fewer than half. That is not a small miss, it is a genuinely gaping hole. And the objects we have missed are not random. They are skewed toward the dark, the faint, and the hard. The bright ones stood out and got found early. The dark ones blended into the black and slipped through, so the ones still missing are, on average, the sneakiest kind, which is the same kind the Dinosaur-Killer belonged to. The census is not just unfinished, it is unfinished in the worst way. Let me set that failure beside the new discovery. The study says the deadliest impactor was dark and dry. Our surveys say the dark ones are the hardest to find, so the type we most need to catalogue is the type we miss. That is not simply bad luck, it is a structural blind spot. Our tools were built for bright rocks in the night sky. The killer wears the one disguise those tools cannot pierce. Fixing that means changing how we look, not just how hard. And that is exactly what the next mission is meant to do. Why is finding them so genuinely hard? The mission scientists have been strikingly blunt about it. Many of these objects are dark, and spotting them is a real challenge. Amy Mainzer leads NASA's next asteroid hunting telescope. She has literally held up a dark meteorite before a congressional committee. Her point was simple. This is how black these rocks are. This is why you cannot see them with ordinary telescopes. Add that ground telescopes are blinded by daylight and glare. They largely cannot look near the sun at all, so a whole slice of the sky is simply off limits. Now the good news, and its immediate sharper catch. We are finally building a mission to fix this exact blind spot. It is called the Near-Earth Object Surveyor, and it hunts differently. It does not rely on catching reflected light at all. It hunts heat as an infrared space telescope. Every asteroid absorbs sunlight and warms up, however dark it is, and a warm object glows in the infrared, no matter its colour. A charcoal rock, invisible in normal light, shines clearly in heat. So the infrared telescope sees the dark ones and the bright ones alike. It sees the exact population we have been missing for decades. Let me explain where this telescope will actually sit. It will fly to a stable point between Earth and the Sun. That point lies about 1.5 million kilometres away. From there, it can watch the sky without Earth's day-night limits. It can even look toward regions that ground telescopes never reach. And it works in infrared, so darkness of colour cannot hide a rock. Remember the charcoal meteorite held up before Congress? In visible light, that rock nearly vanishes against the black sky. In infrared, that same rock glows with its own absorbed heat. So the surveyor turns the killer's best disguise into a beacon. Think about how much that single shift matters. For decades, darkness has been the asteroid's perfect camouflage. The blacker the rock, the safer it was from our eyes. Infrared flips that logic completely on its head. The rock still absorbs sunlight, no matter how dark it looks, and whatever it absorbs, it must radiate back as heat. So the darkest, most dangerous rocks glow the clearest in heat. The camouflage becomes a signal we can finally read. That is why this one telescope carries so much weight. It is aimed squarely at the population we fear most. The plan is to work through the dangerous population fast. Within 5 years, it aims to find most mid-sized near-Earth objects. Over more years, it pushes toward that 90% goal. The goal Congress set 2 decades ago, and we never met. This is the instrument meant to finally finish the census. It is the answer, on paper, to the blind spot we described. But paper is not the same as a telescope in space. A plan on the ground catches no asteroids at all. The mission has faced delays and budget pressures as missions do. Every slip in its schedule is a year of open sky, and the sky does not pause while we sort out funding. So the race is real between the build and the unknown rock. We are trying to open our new eyes before we need them. Whether we win that race is still being decided. And that is where the comfort runs out, hard, and the reason is simple. The telescope has not launched yet. The current schedule sets its launch no earlier than September of 2027, so the blind spot is still wide open tonight as you watch. The study naming the dark rock as the killer came out 5 days ago. The instrument to close the blind spot is still on the ground. Feel that timing. The the warning and the vulnerability arriving together, and finding these objects is still only half of any defence. Suppose the telescope launches and finds a dark rock heading our way. Finding it means nothing unless we can also move it. So the next question is whether we could push it at all. And to answer that, we have to talk about the night we tried. Part 11. The direction we cannot watch. Let me dwell on that sunward blind spot for a moment. It is the single most exploitable weakness in our current watch. And it is not hypothetical, because it has already happened. A ground telescope can only work at night, facing away from the sun. It looks into the dark half of the sky, not the bright half. Any object approaching from the sun's direction hides in the glare. It is the same as a car coming at you out of a low sunrise. You do not see it until it is almost upon you. Every driver knows that blinding, dangerous moment. The car is there the whole time, but the glare erases it. Our telescopes face that same erasing glare toward the sun, and a rock hidden in it is a car we never see. By the time it clears the glare, it may be too late. That is the sunward blind spot in one everyday image. It is not a small gap in an otherwise perfect watch. It is a whole doorway left unguarded in the sky. And the new study tells us who might come through it. The dark, primitive rocks are the deadliest of all. They are also the faintest and the hardest to catch. Pair that faintness with a sunward approach, and you are blind. A dark rock in the glare is a threat doubled. It hides by colour, and it hides by direction, at once. That is the exact profile of the Dinosaur-Killer. So the doorway is not just open, it is the killer's own favoured door. Chelyabinsk did exactly that in 2013. It came in from the daytime sky, straight out of the sun. Not a single telescope on Earth saw it beforehand. The first anyone knew of it was the blinding flash overhead, and it is not some rare one-time fluke either. In recent years, city block-sized asteroids have slipped past us unseen. Some were discovered only afterward, on their way back out. They approached from the sunward side and stayed invisible until behind us. Think hard for a moment about what that actually means. For a certain slice of the sky, our warning time is negative. We find out after the object has already gone by. Now combine that geometric blind spot with the compositional one. Combine the sun's glare with the darkness of carbonaceous rock, and you have described something close to a perfect predator. Dark, so it reflects almost no light to any telescope. Approaching from the sun, so even that faint glint is drowned out. That is not a monster I invented to frighten you. It is a plain description of the rock that killed the dinosaurs, arriving by the one route we cannot watch. Let me explain the geometry of that glare more carefully. The sun is far brighter than any asteroid could ever be. Point a telescope near it, and the glare simply swamps everything. So a wide cone of sky around the sun stays hidden. Objects inside that cone are effectively cloaked from the ground, and objects on approach from the day side sit right in it. An asteroid drifting toward us from sunward can hide for weeks. It only becomes visible once it swings into our night sky. For some paths, that reveal comes far too late to matter. There is a chilling phrase for this among astronomers. They speak of objects with negative warning time. It means we detected the rock only after it passed us. The warning arrived after the danger was already gone. Imagine a smoke alarm that sounds the day after the fire. That is what a sunward approach can do to our watch, and it is not rare in the small size ranges. Every year, objects slip by us and are found later. Most are small and harmless, which is our good luck, but the same blind spot would hide a larger one too. The geometry does not care how big the rock is. It only cares which direction the rock came from. Chelyabinsk is the case study nobody wants to repeat. That 20-meter rock injured about 1,500 people. It damaged thousands of buildings across the city in seconds, and it did all of that with 0 seconds of warning. Now recall that Chelyabinsk was small, only 20 meters wide. Imagine the same blind approach by an object 10 times larger. That is the scenario the sunward gap quietly allows. There have been genuine near misses that drive the point home. Astronomers have spotted house-sized rocks only hours before they passed. Some larger ones were found only days after slipping by us. In those cases, our detection worked, but far too slowly. The rock had already come and gone before we knew it. Think for a moment about how strange and unsettling that really is. We pride ourselves on watching the sky with great care, yet a whole direction of that sky remains a blank. Let me name the deeper asymmetry hiding in all this. We can only easily see objects out in our night sky, but an object on a collision course often comes from sunward. It rides in with the sun's glare wrapped around it, so the most dangerous approach angle is also the most hidden. That is a cruel piece of geometry to be stuck with. It means our watch is strongest where the danger is weakest, and our watch is weakest where the danger is strongest. A space telescope near the sun could help close that gap. It could look back toward the day side we cannot see. That is part of why moving our eyes off the ground matters. From out in space, the blind spot shrinks considerably, but until such eyes are flying, the gap stays open, and a dark rock in that gap gives almost no warning. This is why the timing of the new study matters so much. The forensic record just flagged the dark primitive rocks as deadliest, and those are precisely the rocks that hide best in glare. Low reflectivity plus a sunward approach is the worst possible pairing. It is a killer optimized by pure chance to evade our eyes. Hold that image because it reframes the whole modern threat. The danger is not only that big rocks exist out there, it is that the deadliest kind is the hardest to see, and the hardest to see can arrive with no warning at all. No warning means no time, and time is the entire game, which brings us to the one time we actually fought back, because in 2022 we stopped just watching the sky. For the first time ever, we reached up and struck it, and what we learned should thrill you and worry you at once. Part 12. The night we punched an asteroid and it moved. On the 26th of September, 2022, we did something unprecedented. For the first time in the history of life, we moved another world. The mission was called DART, and the idea was blunt. It was humanity throwing a punch at the sky. The target was a small asteroid named Dimorphos. Dimorphos is about 160 meters across. It orbits a larger asteroid called Didymos, around 780 meters wide. Neither of them was any threat to us at all. That was the entire point. A safe test on a harmless target. Dimorphos was chosen because its orbit is tidy and measurable. Before the impact, it circled Didymos every 11 hours and 55 minutes. If we could change that timing, we would know we had succeeded. The spacecraft itself was not large, roughly the size of a small car. We flew it straight into Dimorphos at around 22,500 kilometers per hour. One deliberate high-speed collision, aimed with great care. Then astronomers watched, timing the asteroid's new rhythm from Earth. They measured the tiny dips in brightness as the pair crossed. And the result blew past everyone's expectations. NASA had defined success in advance as a modest change. Any shift in the orbit of 73 seconds would count. Just over a minute was the bar to clear. DART did not clear that bar by a little. It cleared it by more than 25 times over. The orbit of Dimorphos shortened by about 32 minutes. Later, refined analysis put it near 33 minutes. For the first time, we had purposely changed an object in space. The punch landed, and the sky moved further than we dared hope. Take a moment to feel how big that achievement is. For 4 billion years, life was helpless against the sky. Every rock that ever came simply arrived, and struck, and killed. No living thing could reach up and change its path. And then, on one night, in 2022, that changed. a species reached across space and shoved a moving world. The shove was small, but the principle was enormous. It proved the sky is no longer entirely beyond our reach. That is a genuine turning point in the story of life. It is one of the most important things our species has done. But now the part that ties back to a dark rock. Why did DART work so much better than predicted? When it hit, it did not just transfer its own push, it blasted a huge plume of rubble off the asteroid's surface. That ejected debris acted like a rocket exhaust in reverse. The recoil shoved the asteroid even harder the other way, so the deflection depended heavily on the target's specific material. Dimorphos turned out to be a loose pile of rubble. Hitting a rubble pile threw off lots of debris and lots of bonus push. The European Space Agency has now sent a follow-up called Hera. Hera is travelling out to study the crater dart left behind. Because we changed that orbit without fully seeing what we did up close. Hera will turn a single spectacular result into understood engineering. It will measure the crater dart left in fine detail. It will weigh Dimorphos and map how much we moved it. That matters, because one success is not yet a reliable tool. We changed the orbit, but we watched from far away. We never saw up close exactly what our punch did. Hera fills in that missing picture, piece by piece. It turns a lucky first strike into repeatable knowledge. And repeatable knowledge is what a real defence requires. But notice the gap that even Hera leaves open. Both DART and Hera study a stony, rocky body. Neither one touches a dark, carbon-rich chondrite, and that is the very type the new study flags as deadliest. So our one proven method has never met its worst target. We are learning to move the rocks we understand best. The rocks we understand least are the ones we most fear. That gap is not a footnote at all, it is the whole problem. So sit with the strange shape of where we stand. We have proven we can move a world, which is astonishing, and we have proven it on the wrong kind of world. We can push the rock we understand, not the one we fear. It is like learning to swim in a calm, warm pool. Then being told the real test is a cold, wild sea. The skill transfers, but the conditions are unknown, and you would rather not learn them during the emergency. So the triumph is real, and the gap is real, together, but notice what both DART and Hera studied. A stony asteroid, a rubble pile, not a dark carbonaceous body. And here is the question the Chicxulub study forces on us. What if we must deflect a dark, primitive, carbon-rich object instead? We have never once hit that kind of body. We do not know how that material behaves under our punch. A carbonaceous body can be soft, porous, and crumbly. Deflecting a solid stony rock is like hitting a billiard ball. It moves cleanly and predictably, and DART proved we can do it. But hitting a dark, porous body might be like punching a snowbank. The blow could sink in and barely move the thing at all. Or it could shatter into a spray of dangerous fragments. Let me make that uncertainty concrete, because it is the crux. DART succeeded partly because it threw off so much debris. That debris flew off the surface like exhaust from a rocket, and the recoil from it more than doubled the push. But that bonus depended entirely on Dimorphos being a rubble pile. Hit a different structure, and you get a different result. A dense, solid rock might throw off far less debris. A soft, porous rock might swallow the blow and barely move. We simply do not know, because we have not tested it. Every kinetic strike we model rests on that one real experiment, and that experiment used a stony rubble pile, not a dark chondrite. So we are extrapolating from a single data point. That is thin ice on which to rest a planet's defense. This is why the composition finding is not academic at all. It tells us the objects we most need to move are the untested kind. Dark, primitive, porous, and utterly outside our one experiment. We may need to learn their behaviour before we ever need it. Because you cannot run a first test during a real emergency. So the punch worked once, and that is a genuine triumph. But the next target may not answer to the same punch. We know how to move the bright, hard rocks now. We have never moved the dark, primitive kind that ended the dinosaurs. So how do we even know all of this ancient detail? The answer is a detective story that ran for 45 years. Part 13. The 45-year hunt for a hidden crater. Everything I have told you rests on a discovery once thought absurd. The story of how it won belief is worth your time. It is the story of how we learned to read the sky's fingerprints. Go back to the year 1980 for a moment. A physicist named Luis Alvarez worked with his geologist son Walter. They were studying that thin boundary clay, exposed in an Italian gorge. They were chasing a simple, almost innocent question. How long did that layer of clay take to form? Their clever idea was to measure iridium inside it. Iridium rains from space and cosmic dust at a slow, steady rate, so the amount in the layer should act like a clock. More iridium would mean more time had passed, in theory. But what they found broke the clock entirely. The iridium was not slightly high, it was wildly, impossibly high. It ran dozens of times above the normal background level. No slow rain of cosmic dust could ever explain that. Only one source made sense for so much iridium at once. A large extraterrestrial object had struck the Earth. It had vaporized and spread its metal-rich guts across the globe. Iridium is rare in Earth's crust but common in asteroids. That contrast was the original smoking gun. And so the impact hypothesis was born from a broken clock. Now here is the part people forget about this story. The reaction from many scientists was sharp skepticism. Paleontologists had spent careers building slow, gradual explanations. Slow climate shifts, changing seas, and gentle declines over ages. The idea of death in a single instant felt like fiction. The debate ran hot and bitter all through the 1980s. And the impact theory had one obvious, damning hole. If a giant object hit, then where was the crater? Show me the hole, the critics said, again and again. It took nearly a decade to answer that challenge. The crater was hard to find for a simple reason. It was buried under the Yucatan and the shallow sea. It was invisible at the surface, hidden from plain sight. Its shape showed only in gravity and magnetic data. Oil company geologists had gathered that data years before. They had no idea what they were actually looking at. Around 1990, the pieces finally came together. The Chicxulub crater was confirmed as the impact site. It had the right size, the right age, the right place. The skepticism did not vanish overnight, but the ground shifted, and the crater did not stand alone as evidence. Scientists returned to that boundary layer worldwide, now knowing what to seek. They found the fingerprints an impact cannot help but leave. Tiny glass spheres, droplets of rock melted and flung skyward, grains of shocked quartz deformed by pressures only impacts create. Ordinary volcanoes cannot make that quartz, and only a great blow can. And the global iridium, the vaporized impactor, sprinkled worldwide. Each was an independent clue, and all pointed the same way. A single sudden strike at the exact moment the dinosaurs vanished. That is how a fringe idea becomes a hard consensus. Not one dramatic proof, but many clues telling one story. Let me note what that shift did to science itself. For a long time, catastrophe was almost a forbidden word. The dominant view was that Earth changed only slowly. Mountains rose over ages, and species faded over ages. The idea of sudden, violent, global change felt unscientific. The Alvarez discovery cracked that comfortable assumption open. It showed that a single day can rewrite the whole planet, that the sky itself can reach down and end an era. And that realization did more than solve one mystery. It made us take the threat from space seriously at all. Without it, there would be no asteroid surveys today, there would be no DART, and no infrared telescope planned. The whole field of planetary defense grew from that clay. So the detective story did not just explain the past, it woke us up to a danger still hanging over us. The people who read the iridium changed how we see the sky. they turned a dead extinction into a live warning. And that warning is why the newest chapter matters so much. The same lineage that found the crater now reads the chemistry. Each generation of scientists sharpens the picture a little more. 1980 gave us the iridium and the idea. 1990 gave us the crater and the proof. 2024 gave us the origin beyond Jupiter. 2026 gave us the dry rock and the dust. 4 discoveries, 4 decades, 1 unbroken chase. And that chase is not a museum piece, it is still ongoing right now. Right now, someone is planning the next measurement. Someone is asking what the clay has not yet revealed. So the detective story runs on into our own time. The nickel study from 5 days ago is the newest of them. It reads the same event with a sharper instrument than before. Let me lay out that lineage, because it is one continuous chase. First, the iridium, which told us something struck the Earth. Then the crater, which told us where and how large. Then, in 2024, the ruthenium, pointing beyond Jupiter. Then, in 2026, the nickel, naming a dry CO chondrite. And that dryness points in turn to the dust as the killer. One continuous detective story, 45 years long and counting. The longest cold case in the history of this planet. And I want to be honest about what is still open. The team said the killer was a CO chondrite, or something close. They allowed for some ungrouped primitive chondrites we may not sample. They said most likely, and those 2 words do honest work. We are reading a smear of atoms across 66 million years. There is a little blur at the very edges of the answer. The comet versus asteroid debate leaned hard toward an asteroid, but it existed. And a background stress was already straining that ancient world. Enormous volcanic eruptions in what is now India ran for ages. Some argue those eruptions had already weakened the ecosystems. The strongest position is not impact versus volcano at all. It is that the impact was the sudden, decisive, global blow, and it landed on a world already running a fever. So the case is sharpened, not closed, and the models are being redone. That same detective lineage now turns to face the future. The people reading old clay and the people building telescopes are kin. One reads the fingerprint the killer already left behind. The other tries to spot the next killer before it acts. And they meet at a single word that runs through this whole story. It comes down to composition, what the rock is made of. So let me take that lesson and aim it at our own century. What would a rock like this actually do to us now? Part 14. What a dark rock would do to us now. Let me do what the news coverage mostly skipped. Let me take the mechanism we uncovered and aim it at us. Not the dust and darkness for dinosaurs, but for people. And not with a planet killer, because those are rare and mostly found. Let me use the realistic threat, the middle of the ladder. A dark object a few hundred meters across, hard to spot. Arriving, as we have seen, with little or no warning. Something that size does not end life on Earth. I refuse to trade an apocalypse just to frighten you. It would not throw a 2-year global veil over the sun. But scale the same mechanism down, and it is still a horror. A few 100-meter strike would devastate a region far larger than a city. Strike the ocean near a coast, and the tsunami crosses a whole sea. That is the direct blow, and by now you know the pattern. The direct blow is not the part that should worry you most. Here is the lesson of Chicxulub, boiled all the way down. An impact is not primarily a fire problem at all. It is a food problem, at the base of everything. The thing that killed most of what died was the food supply failing, sunlight into plants, interrupted long enough to break the chain. Now look hard at the world we have actually built. 8 billion people rest on a food system with little slack. Global grain reserves amount to only a few months of eating. We do not keep years of food stored away anywhere. We grow it, ship it, and eat it in a tight, constant cycle. That cycle assumes next season's harvest will simply arrive. Now imagine even a regional impact dimming the sun over farmland. Imagine temperatures dropping across a hemisphere for a season or two. You do not need a 2-year global blackout for catastrophe. You need one failed harvest across the wrong latitudes. Hold that, because history already ran this exact rehearsal. In 1815, a volcano called Tambora erupted in Indonesia. It threw a fine veil of material high into the atmosphere. The next year, 1816, summer never truly arrived. Snow fell in June across parts of North America. Frosts killed crops through the season in Europe and beyond. Harvests failed, prices spiked, and famine followed in many places. People at the time had no idea why the sky was wrong. They only knew the food would not grow. That was one volcano, and a fairly modest dimming at that. It still rewrote an entire year of human history. Now picture that same shock in our connected world. A failed harvest in one region does not stay there. Prices spike, exports halt, and shortages spread across borders. A crisis in a few bread baskets becomes a crisis everywhere. Our efficiency is also our fragility in this one respect. We grow food in a few key places, then ship it worldwide. That works beautifully until one of those places fails. A dimmed sun could make several of them fail at once. And unlike the dinosaurs, we cannot simply burrow and wait. 8 billion people cannot hibernate through a lost harvest. So the danger is not fantasy, and it is not distant biology. It is a stress test our food system has never faced. And it is a test we would rather never sit at all. Which is why finding the rock early is everything. A harvest saved is a harvest never even threatened. Move the object years out, and no crop ever fails. That is the whole promise of a working watch. It does not merely fight the famine, it prevents the famine entirely. So the fight against starvation begins at a telescope. It begins years before any rock ever nears us. Now scale that lever harder, with an impact behind it. So the real modern danger is not what you would guess. It is not the crater, and it is not the fireball. It is the harvest, failing suddenly across the world's farmland, in a system that keeps only months of food in reserve. That is why detection and deflection matter so desperately. Because the whole game against this threat is buying time. Find a dangerous object decades early, and deflection is almost gentle. A small nudge, applied early, clears the earth completely. Let me make that physics concrete, because it is the hopeful part. Picture aiming a rifle at a target far downrange. Shift the barrel a hair, and the shot lands far away. That tiny angle multiplies across the whole distance to the target. Deflection works the same way, run in our favour. Nudge an asteroid gently decades before it would arrive. Change its speed by a mere whisper, a few centimetres per second. Over years and millions of kilometres, that whisper becomes a clean miss. The Earth simply is not there when the rock crosses our path, but that gentle magic only works if you have the years. Push a rock a decade out, and a feather saves a continent. Push it a week out, and there is almost nothing to be done. There is no distance left for the small change to grow. Let me underline how fragile our food system really is. It is a tight, global web of planting, shipping, and eating. It assumes stable weather and a reliable growing season. It assumes ports stay open and harvests arrive on time. A sudden dimming would strike every link in that web at once. Failed harvests in one region ripple out to hungry regions far away. The buffers we keep are measured in months, not years. The Chicxulub mechanism, though, works on the scale of years. That mismatch is the exact danger we should be planning against. Not panic, but sober, forward-looking preparation and detection. Because the cheapest defense of all is simply early warning. An object found decades out can be nudged with a feather. An object found weeks out can only be watched as it comes. So the whole fight comes down to seeing the thing early. And seeing the dark ones early is precisely our weakness. This is why the new study lands with such weight. It tells us the deadliest rock is the one we see worst. So the value of every telescope is measured in one currency. That currency is warning time, and nothing else. Every year of notice turns the impossible into the routine, and warning time is exactly what the dark, sunward rocks steal. Which raises the last question before we bring the clocks together. Who, right now, is actually keeping this watch for us? Part 15. The watch running while you sleep. Right now, as you watch this, systems are tracking the sky. This is not hypothetical, and it is not science fiction. It is operational, it is real, and it has a specific shape. At its centre sits a group at NASA's Jet Propulsion Laboratory. It is called the Centre for Near-Earth Object Studies. Their job, in plain terms, is to keep the ledger. Every known near-Earth asteroid, its orbit, and its future close passes. They compute and recompute those paths as new data arrives. They run an automated system named Sentry to watch for danger. Sentry scans the whole catalogue of known objects continuously. It flags anything with even a tiny chance of hitting us. And it assigns real, specific numbers to that risk. Across the Atlantic, the European Space Agency runs its own list. It tracks the same threat from a second independent vantage point. Two ledgers, cross-checking each other, watching the same dark sky. And there are other tools in this quiet arsenal. When an object passes close, we can hit it with radar. Radar can map an asteroid's shape, spin, and exact path. It turns a faint dot into a known, measured world. For years, a giant dish in Puerto Rico led that work. That telescope at Arecibo collapsed in 2020. Its loss was a real blow to how we study close objects. Other dishes carry on, but the gap was felt sharply. This watch is also a global effort, not one nation's alone. Observatories on many continents feed the same shared catalogue. Astronomers around the world track new objects together. There is even a recognised day each year for this threat. It exists to remind people that the danger is real. So the watch is broader and older than most people know. It has been quietly running for decades already. But breadth and history do not fix the core weakness. We have watched the sky for decades, and watched it well. Yet the census of dangerous objects is still half empty. All that experience cannot find what it cannot see. And the dark rocks stay just beyond our reach. So the age of the watch is not the same as its completeness. We have the ledgers, the radar, and the global network. What we lack is the power to find the faint ones early. That single missing piece defines the whole risk. So the watch, for all its strengths, has one true flaw. It can follow a rock, but not conjure one it never saw. And the hardest rocks to see are the ones that matter most. The dark ones, the sunward ones, the quiet ones. Those are the objects our watch is built to miss. Until we fix that, the ledger will stay incomplete. And an incomplete ledger is a door left ajar. Most of what they track is reassuring, in a precise way. Nearly all the true giants, a kilometre and larger, are found, and none of the known giants is on a collision course. Take that comfort, because it is real and hard won. But do not settle into it, because a larger question waits. The giants are found, yet the middle of the ladder is not. Those few 100-metre objects are the ones we keep missing. So let me show you how the system rates a threat. When a risky object appears, astronomers place it on a scale. It runs from 0 to 10 and is called the Torino scale. 0 means no concern, and 10 means a certain global catastrophe. And one object has climbed higher on that scale than any other. Its name is Apophis, and its story shows the system working. Apophis was discovered back in 2004. The early orbit could not immediately rule out an impact. For a tense stretch, it climbed to Torino level 4. That is the highest rating any asteroid has ever reached. It meant the whole world's astronomers should pay attention. And then, the system did exactly what it was built to do. More observations came in, and the orbit sharpened. The impact possibilities were eliminated, one after another. Apophis dropped all the way back down to 0. The scare resolved not by luck, but by looking harder. Looking turned a frightening uncertainty into a confident all clear. And Apophis still has a remarkable appointment with us. On Friday the 13th of April, 2029, it returns. It will pass closer than the satellites in high orbit. Let me be absolutely clear about this, to prevent any panic. Apophis will not hit us in 2029, and that is fully ruled out. It will miss, but it will pass astonishingly close. Close enough to be visible to the naked eye from Earth, a mountain-sized rock, threading between us and our own satellites. But do not exhale yet, because that flyby is a rehearsal. Every telescope and radar we own will lock onto it. We will study how it tumbles and how the sun nudges its path. It is, in a sense, a dress rehearsal for the real thing, a practice run for the day we find one that will not miss. And all of this machinery shares one deep limitation. It is superb at tracking objects once they are found. Give it an object, and it will map decades of its future. But it can only track what we have already detected. And detection, as we have seen, is the weak link. Especially for the dark ones, hiding in glare and in shadow. So the watch is real, and it is genuinely impressive, but it has a blind spot shaped like the Dinosaur-Killer. Let me show you how good that tracking has become. Once an object is found, its future can be predicted for decades. The math of orbits is precise and deeply reliable. That is why the Apophis scare could be resolved so cleanly. More data, sharper orbit, and the risk fell to 0. The system is not guessing at all, it is calculating with great care. But every one of those calculations needs an object to start. It needs a rock that has already been detected and measured. Sentry cannot flag a danger it has never seen. The Torino scale cannot rate an object nobody has found. So the entire apparatus of assessment has one hard requirement. We must first spot the object, early, out in the dark. And for the dark sunward rocks, that first step often fails. This is the gap the whole story keeps returning to. We can track almost anything, but we cannot yet find everything. The finding, not the tracking, is where we remain exposed. The most valuable thing we could build is not a better tracker. We already track very well, but we need a better finder instead, and that is exactly where the next few years are meant to take us. So let me bring the two halves of this story together at last. Part 16. The two clocks racing toward the same rock. Picture two clocks running at once, because that is the real structure. The first clock is the forensic clock, and it runs backward. It started ticking 66 million years ago, at the impact. Every advance in our instruments reads a little further along it. Iridium, then the crater, then ruthenium, then nickel. That clock tells us what happened, and how it happened. 5 days ago it ticked forward and told us the composition. Dark, dry, carbon-rich, and born beyond Jupiter. Killed mostly by dust and darkness, not by fire and sulfur. The second clock is the defense clock, and it runs forward. It counts down toward an event that has not happened yet. That event is not a question of if, only of when. That clock is measured in telescope launches and survey progress. It ticked in 2022 when DART moved a rock. It is set to tick again in 2027 when the Surveyor launches. Every object we catalogue moves that clock in our favour. Now here is the thing that should hold your attention. These two clocks are not independent of each other at all. They are wired together, and the wire is composition. What the forensic clock learns decides what the defense clock must fear. Follow that logic all the way through with me. The forensic clock says the deadliest impactor was dark and carbon-rich. The defense clock asks which objects it is worst at seeing, and the answer comes back the same: dark, carbon-rich bodies. It asks which objects it has never tested a deflection against, and again, the answer is the same: dark carbon-rich bodies. The past is describing our present blind spot in chemical detail. That is the convergence at the heart of tonight. Not two events landing in the same news week, but two timelines, 66 million years apart, pointing at one rock. The forensic timeline says this is what killed everything before. The defense timeline says this is what I can least afford to miss. And they are describing the very same kind of object. Think about how rare a gift that specificity really is. History usually teaches in vague generalities we can ignore. Be prepared, expect the unexpected, and other empty wisdom. But this is not that at all. It is a precise technical warning. The deadliest impactors are dark, dry, and hard to see or move. That is an intelligence report, 66 million years in the making. Delivered by a team measuring nickel atoms in old clay. The clay remembered what the killer was made of, and what it remembered maps onto our weakest point exactly. So let me stack the danger into its real layers. The top layer is the impact. The fireball everyone pictures. It is real, but near the strike, and globally it is local. Beneath it lies the second layer, the dust and the long dark. That layer did most of the killing, and it hid for decades. Beneath that lies the third layer, the composition itself. Dark and carbon-rich, the exact thing we cannot easily see, and beneath even that lies the deepest layer of all. That deepest layer is not made of rock or dust, but of pure attention. Whether we keep watching decides whether the other layers reach us. That layer runs on human memory, not on orbital mechanics. And human memory is painfully short against a threat this slow. Consider how quickly a scary headline fades from view. An asteroid makes the news, and for a week we care. Then the next story arrives, and the sky is forgotten. But the telescope still needs building, year after year. The catalogue still needs finishing, long after the fear passes. That is the trap of a slow, patient danger. It never feels urgent on any single ordinary day. So the work of watching must survive our own forgetting. It must outlast news cycles, elections, and shifting budgets. That is genuinely hard for a species built for the moment. We evolved to fear the predator in the grass. We did not evolve to fear a rock a decade away. Yet the rock a decade away is the one we can still stop. The threat moves on the clock of geology across millions of years. Our attention moves on the clock of the news cycle across days. That mismatch, more than any rock, is what should worry us. Let me say what this convergence should actually change. It should change what we choose to look for first. The warning points, straight at the dark, primitive bodies. So the infrared surveyor becomes not a luxury but a priority. It is the one tool that sees those exact rocks well. The warning should also change how we test deflection. We proved the punch on a bright, stony rubble pile. The next test should target the dark, carbonaceous kind, because that is the material the record flags as deadliest. We should learn to move it before we ever must, and the warning should change how long we stay committed. This is not a threat you solve in one budget cycle. It is a watch you keep across generations, patiently, that is the hardest ask of all, and I will be honest about it. Because a defense that works leaves nothing to show for itself. No impact, no crater, no disaster, and so no headline. The reward for success is a quiet sky and an ordinary day. That is a very hard thing to fund year after year. Yet it may be among the most important things we do. Let me stack the danger into its true layers once more. The top layer is the impact, the fireball everyone imagines. Beneath it lies the dust, the long dark that did most killing. Beneath that lies the composition, the dark rock we cannot see. And beneath all of it lies the layer of attention itself, each layer hid under the louder one above it. And the deepest layer is the quietest and most decisive. That deepest layer is not physics, it is whether we choose to look. That is the strangest part of this entire threat. The rock is real, but our attention is the true variable. A telescope unfunded is as dangerous as a rock unseen. So the convergence is not just a fascinating coincidence, it is a to-do list handed to us by deep time. And it is a list with no deadline printed on it. That is what makes it so easy to set aside. There is no date, no countdown, no ticking alarm. There is only a certainty that the day will come. Someday, on the long clock, a dark rock will find us. The list tells us how to be ready when it does. Find the dark ones, test the punch, and keep watching. None of that is impossible, and none of it is cheap. All of it depends on caring before there is a crisis. That is the hardest instruction on the whole list, and whether we act on that list is still open. So the two clocks are still running, right now tonight, and the space between them is where our whole future sits. Part 17. The most dangerous moment is the quiet one. Let me take you back to that thin, dark line in the rock, the one you can press your finger against on a cliff. When we began tonight, it was only a line. Below that line lie the dinosaurs, and above it lies a world emptied out. But look at that line now, knowing what you know. It is not merely the record of an ending. It is a message written in the only ink deep time uses. That ink is residue, the leftover atoms of a catastrophe. Everything we learnt tonight came out of that single seam. The iridium that first whispered that something had struck. The nickel that finally named what the killer was. The dust, measured grain by grain, that showed how it killed. 66 million years of silence, held in a band of clay. And the whole story was waiting there the entire time, waiting for a species patient and clever enough to read it. The line is not the end of a story at all. It is the fingerprint the killer could not help but leave. 5 days ago, we read the last letters of its name. Think of the strange chain that clay passed through to reach us. It settled from a poisoned sky onto a dying world. Then it waited, through the long rise of the mammals. It waited through ice ages coming and going. It waited through the whole of human history, through language, through writing, through the very first telescopes. It sat in cliffs that no one understood for ages. Until, in 1980, we finally asked it the right question. And then, decade by decade, we built sharper ears to hear it. The dinosaurs left no warning, because they simply could not. But the impact that killed them did leave one behind. It signed its work in iridium and nickel and shocked quartz. It laid that signature across the entire planet at once. And that signature was a message to whoever came next. To whoever grew clever enough, one day, to read it. We are whoever came next, and that is the strange, humbling truth. And the message, decoded at last, is not about the past. It is a description of exactly what to watch for. And that is a stranger inheritance than it first sounds. The killer told us its nature, without meaning to. It left a map of the very thing that could return. Dark and dry and hard to see against the black. The clay did not just record a death, it also handed us a warning aimed at whoever grew wise enough to read it. Remember who we were when that rock came down. Our ancestors were the small things hiding in the dark. They survived not by strength, but by being overlooked. They powered down, burrowed, and waited out the long night. Everything we are traces back to those overlooked survivors. And look at what the overlooked survivors have become. Their descendants read the killer's name from a smear of clay. They traced its birthplace to a cold region beyond Jupiter. They even reached up once and moved a rock into space. No other species that ever lived could do any of this. Every earlier extinction fell on a world that never saw it coming. The trilobites did not see their catastrophe coming. The dinosaurs did not see theirs coming either. For 4 billion years, life was blind and at the sky's mercy. Then, in a few short decades, one species crossed a line. We became the first life that can look up and understand. The first that can calculate a path and perhaps change it. That is not a small thing at all. It may in fact be everything. And it places a choice in front of us that the dinosaurs never had. They could only wait, blind for whatever the sky sent. We can look, and measure, and perhaps even act in time, but looking is a choice we have to keep making. The sky does not care whether we keep watching or not. The rocks will keep drifting, seen or unseen, either way. Only our attention decides whether we meet them ready. So here is the one question this whole story turns on. We were wrong about what the Dinosaur-Killer was made of. So are we also wrong about what the next one would do? And could we even see it coming before it reached us? I told you at the start I would not pretend to answer. The clay has told us what kind of rock to fear. It has told us the dark ones are the deadliest. It has told us they are the hardest to see. But whether we act on that warning is still unwritten. The telescope built to find them has not launched yet. Tonight, the blind spot is still open above us. There is still a direction of the sky we cannot watch, and out there, dark and quiet, the next rock may already be moving. The dinosaurs never had the chance to look up. We can, and we are the first ones who ever could. 5 days ago, we learnt the true name of their killer. In the same breath, we learned its kind is our blind spot. The forensic clock and the defense clock are both still ticking. The next chapter is being written right now, as you breathe. In a launch schedule, in a survey, in a rock not yet found. The most dangerous moment was never the fire in the sky. It was the long, quiet dark that came afterward. The part no one was watching, when the real dying happened. That is the pattern. 66 million years ago and today. The danger is not the flash we all brace for. It is the silent thing that comes when attention fades. So the clay has done its part and handed us the warning. The rest of the story is still ours to write. And it depends on one simple thing, starting tonight. And it all comes down to whether we keep looking up